A half-hour discussion of funny people on the other basketball team. Okay, so what we're going to start off today with is a concept about Lewis structures, which they're sometimes called resonance structures. And the idea is that sometimes we can draw more than one correct Lewis structure. So sometimes there's more than one good Lewis structure. And so what do you do if there's, potentially more than one right structure? One of the ones you guys should have come across was something that looked like this. And so this is the NO3 minus anion. Oops, those brackets are different sizes. That bugs me. And the question is, or if we look at it, there's two bonds that are just single bonds between nitrogen and oxygen, and there's one bond that's a nitrogen-oxygen double bond. Oops, I forgot some electrons on this oxygen, and I didn't finish off those other ones either. Let's see, everyone's got 8, so that's good. So this is what we would draw, and we see that there's two different types of bonds. But if we do an experiment, and one of the things we should always remember, especially with any model we have, if we have an experiment, the model has to explain it, and if the model can't explain the experiment, we have to modify the model. We can't really modify the experiment. So if we do an experiment and measure the bond lengths, or measure the distance between the atoms, all three are the same, which is strange because we would expect a carbon or a nitrogen-oxygen double bond to be shorter than a nitrogen-oxygen bond. And so the way we can explain this, and it also helps to explain a bunch of other cases where it is potentially possible to draw more than one correct Lewis structure, meaning which atom you draw a double bond to matters, is by that concept of resonance. And so what we say is that that picture and this picture also exists. And it's going to seem a little silly for this example just because it's kind of an easy example. But instead of having the double bond going up, let's have the double bond go to the left. And we can even draw a third picture where we have the double bond going to the right. So we're saying that we can tell the difference between whether the double bond is to the left, to the right, or straight up as I drew it. Oops, -1, -1. Draw some more dots, leave some room for the dots. Like this. And so what resonance says is that all three structures are possible. And different. Therefore, the real Lewis structure is a superposition of all three. Or, if you want, we can say like a combination of all three Lewis structures. And I'll draw that in a second since I ran out of room on this. I won't try to scrunch it in the corner or something weird like that. I'll just pause for a second. Now, this is, of course, predicated on the fact that the atoms are connected together in the same shape. Meaning, if you have a model where you draw a Lewis structure and one person connects the atoms together in one way and another person connects the atoms together in another way, that's not an example of resonance because you can't really break and change the bondings. But if you have a single bond versus a double bond or something simple like that different from someone else's model, we have to realize that they're all three the same thing. So if I grade your homework and, Cody has the first one and Alyssa has the middle one and, Aaron or someone has the third one, well, you might compare answers to each other and go, oh, they're different, right? So how do we all get it right? Or you might look at it and say, well, one of us must be wrong, but realize all three models are the same molecule, right? Where we draw that double bond doesn't matter. In fact, we're also going to learn that sometimes how we even draw it, like for instance, what if someone drew it like this and just made them, kind of a different angle between everything. Is that any different than the other two models? No. So realize that there's about 1 million different ways to draw these molecules. And so if you're comparing notes with someone else, you know, with a grain of salt, look at it and go, oh, they really are the same maybe. Okay, so the idea is that all three models, if we draw the superposition, or basically if I kind of think about all three happening at once, what we're going to say is that each of the oxygens is bonded by one nitrogen, and then each of them also has kind of like a 1/3 of a bond. And so then all those bonds are equal. And then if we think about the electrons around them, and you really can't count electrons at this point. You know, so we're going to have kind of octets around all of them. And so it's more like each one is connected by, say, 1 1/3 of a bond instead of, you know, 1 double bond and 2 single bonds. And here's where it goes beyond the scope of what we care about, meaning we want to realize that these superpositions can occur, mostly because we want to realize that people can have different Lewis structures or small modifications of Lewis structures for each other, and then realize that really it's the tip of the iceberg. To really truly understand this, you're going to have to take a look at the actual shape or what happens with the s, p, d, and f orbitals. And there's a theory beyond Lewis structures, which is called valence bond theory, and then there's a theory beyond that that's called molecular orbital theory, and then there's at that point, you get to the point where you're programming computers to do all the simulations for the shapes and what happens with the electrons around the atom. So it quickly becomes very complicated. But the nice thing about Lewis structures is it's pretty accurate at telling us whether a molecule is going to exist or not. Meaning if we can draw a molecule that everyone has octets and we don't violate any of the really weird rules like, you know, trying to make 3 bonds to fluorine or 2 bonds to hydrogen, then we're pretty sure that molecule exists. And if we can't draw a very good Lewis structure, then we're pretty good sure that molecule doesn't exist. So you guys remember at the beginning of the semester we talked about, we know CO, or we know, like, you know, CO exists, we know CO2 exists, and then I said, well, CO3 doesn't exist, right? And so if you try to draw their Lewis structures, what you'll find is you can draw a Lewis structure for CO2, you can draw a Lewis structure for carbon monoxide, but it's impossible to draw a Lewis structure for CO3 where everyone's octet is satisfied. But, for instance, you can draw CO3 2- Lewis structure where it's an ion, right? And so one of the things we said is that those polyatomics exist, they just don't exist by themselves, they have to be paired up with something, right? So realize that all the molecules I gave you to memorize and saying they exist, you should be able to draw a good Lewis structure for. And now in the future, if we ever, and we really don't have to worry about it too much in the future, but you know, if you want to see if a molecule is likely to exist or not, you would have to draw a Lewis structure. I should also point out, and we deal with such simple molecules that there's maybe only 1 or 2 cases in your lab or anywhere else where you can draw more than one correct Lewis structure that has different bonding together. That's technically called isomers. They're called structural isomers. That's something that we will deal with in another chapter. For instance, I guess, let me just give one example. So if I draw this Lewis structure, I could also draw that Lewis structure like this, and I think it's the same. I'm doing this one off the top of my head, so I might make a mistake. Meaning that this molecule is C3H12345 and an oxygen, this molecule is C3H12345. Both of those are C3H6O. And those are 2 different Lewis structures, right? One of them has the carbon-oxygen double bond in the middle. One of them has the carbon-oxygen double bond at the end of the molecule. These are what we call structural isomers. If you came across this as a test question or a lab question or anything like that, both answers are correct, even though they're not very close to each other, right? So realize if you are checking answers and things like that, sometimes there is more than one correct answer. Yes, and so for our class, this one technically is probably the better answer, but this is not wrong. That molecule really does exist.
Second semester, we'll talk a whole ton about structural isomers. One of the things we find is that carbon chemistry is very complicated because carbon can form for both single bonds, double bonds, and triple bonds, and it loves to make long chains of carbons. And so the molecules that we have access to this semester for molecular compounds are rather a small assortment. Second semester, we get to the point where there are hundreds of thousands, if not, maybe not quite that many, but certainly there are hundreds of thousands of possibilities for molecules that we could draw in class. We can probably say that in class we can really limit it to a few thousand that we can draw and use and talk about and know and understand. And so second semester we really kind of open that up. Let's take a look at the idea of polyatomic molecules. You guys remember how I defined polyatomics way back whenever it was, in like chapter 5 that we talked about them first, or chapter 6? Nope. Okay, so polyatomics were fragments. Well, we talked about them as being molecular fragments with a charge. Or that the idea is that part of the molecule is molecular and part of the molecule looks like it's ionic. And an example of that would be simply Na2CO3, in that the interaction between the sodium and the carbonate anion is ionic, meaning we know that sodium is +1 and carbonate is -2, but the CO3 -2 part is molecular. And so we've kind of got two different types of things going on. Now, we labeled these as being ionic compounds because we had the metal in them, right? And the majority of the bonding is that ionic because we're really gaining and losing electrons. But really that CO3 is connected together in terms of a Lewis structure. And so we can kind of draw Lewis structures for these, and we kind of have to mix our nomenclature from the ionic ones where we simply show them in brackets, and then we can draw part of it, for instance the CO3 part, like this. And I think that's CO3 2-. I'd have to double check. Let's see. I guess we should do it really quick because I'm just making the molecule up. I should have probably just used the ones from my notes. It's a lot easier to draw if nothing else. Carbon is right. So this interaction here between the sets of brackets is ionic, right? And that CO3 part is molecular, meaning part of the molecule shares electrons and part of the molecule gains and loses electrons.
Why is there 2
To balance the charges, right? So it's Na2CO3. So let's see, oxygen is 6, so that's 18, plus we have an extra 2, so what is that, 24, so 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24. Yeah, that's what I thought it was, just one double bond in there. So realize that we can mix up ionic molecules and molecular compounds kind of in one, and that's our idea of what we really kind of tend to think of polyatomics. And bless you. Okay, now on to geometry. It's not that bad, Taylor. There's a pattern and a trick and everything else to it, okay? So don't worry. Now this molecular geometry will be, I should also maybe have even said this way before when we were talking about Lewis structures. The very first thing we talk about second semester is Lewis structures, so don't forget this stuff. And the molecular geometry we talk about second semester, it's the very first thing. If it's something that you remember, then you get an easy lab that takes you like 20 minutes to do tops. And if you don't remember any of it and have to relearn it, then you get to spend a couple hours relearning it. So this is over the Christmas break, not summer.
That's what I meant when you break.
Okay, so realize that sort of on paper, we draw things in 2 dimensions, right? Sometimes we can try to draw a 3-dimensional look of it, but realize that in real life, or in reality, or I don't know what we want to say, or in the lab, however we want to say it, things are really 3-dimensional. And so we have to think about the shapes in 3 dimensions. while drawing them in 2. And so realize that on a test, you get your molecular model kits. So you'll always have these. They're a very good double check for drawing any Lewis structures, because if you draw a Lewis structure and can't build the model, it probably doesn't work. If you can build the model, the Lewis structure probably will work. And so it's a good double check. Plus, I think the models help you see the three-dimensional geometry much better than trying to draw it on a piece of paper. You have to really use your imagination for that. And so the theory that describes the geometry is called valence shell electron pair repulsion theory. I love it just because it's a mouthful. Valence shell electron pair repulsion. I guarantee you, if your mom and dad ask you what you did today, or anyone else, and you say, well, we learned about valence shell electron pair repulsion theory, they will be like, whoa. Because, I don't know, it just, to me, it always sounds impressive. If we abbreviate it, it's VSEPR, since we'll probably never write valence shell electron pair repulsion theory again. And it's a pretty basic theory. It simply says that electrons want to stay as far apart as possible, or we can maybe say electron pairs want to stay as far apart as possible.
So when we think about molecular geometry, the only rule we truly have to apply is valence shell electron pair repulsion theory to figure out how to keep those atoms as far apart as completely possible. And then the other thing that we have to look at is, there's some patterns to it. So there's only 6 shapes we're going to talk about. Let me double check. Yep, 6. And so you can remember the pattern. You can just memorize 6 things and 6 bond angles. There's a lot of different ways you can approach this. I tend to approach it from a logical perspective and think about it that way. So our basic model, or our first category that we're going to talk about, is things with 4 bonds, because it's probably the most common. And I should say 4 bonds to different, 4 bonds. Yeah. Well, actually, here, let's organize it this way. I always struggle with this because it's terminology. Number of bonds, number of lone pairs. That's probably the easiest way to group it together. Number of bonds to atoms, if you want to say it that way. So the first one we're going to look at has 4 bonds to atoms and no lone pairs on the molecule. And our example for that is just methane, CH4. And you'll also note that I tend to, for my examples, pick the easiest possible molecule to draw, meaning there's lots of other molecules that are like this. And we're going to call this molecule tetrahedral. And here's where we have to distinguish between, that's kind of how I draw it in 2 dimensions, but how does it really look in 3 dimensions? So what I want you to do is go ahead and pull out one of those black atoms and make methane. And you'll notice that the black atoms don't have the holes separated by 90 degrees like that, meaning that's my 2-dimensional picture. If I try to sketch it in 3 dimensions, what we have to realize is that you can kind of think about it as a little pyramid almost, meaning 3 of the bonds are down. And if I kind of shade them differently, then it makes one look like it's kind of coming out of the paper and one going into the paper. And then I can have one up. So that's one way to kind of draw it in 3 dimensions and try to show that shape. I hear lots of bond rattling. I should point out, for the single bonds, remember, use the short little stubby ones, not the long flexy ones. Aaron. Just teasing. I didn't mention that, so we can't expect it. No, but it is a lot easier to see with the short stubby bonds than to see the things with the flexy bonds. So, yes, I have to be honest, everyone loves this part of the lab because they can make pewing sounds. They can make, I have people make dogs and things like that out of it, or just start randomly sticking things together and saying, Jay, does this exist? And things like that. So this shape kind of looks like this should be 90 degrees, but realize that this is really not equal to 90 degrees. Even though we kind of draw it as 90 degrees, that in 3 dimensions, it turns out that this is 109.5 degrees separating those atoms. And so the shape of the molecule we're going to say is tetrahedral, and the bond angle between the atoms is 109.5. And so that means that any atom that you draw that has bonds to 4 atoms, 4 different atoms, and has no lone pairs, has this tetrahedral shape. And then, that's geometry, so take it on faith. Meaning, if you take, no. And realize also when I say bond angles that those are idealized bond angles. For instance, if you take off one of these atoms and say put a different color on there and call it a chlorine or something, then realize that since chlorine is much, much larger than hydrogen, what it would do in real life is it would probably make all of these bonds kind of stretch down. And so some of the bonds would be a little bit less than 109. Some of the bonds would be a little bit more than 109. But the general idea is that we're only worried about the actual idealized bond angles. We're not going to do any calculations to figure out the real bond angles. And really the only reason we need to know the bond angles is because 2 of the models look so similar that almost the only way you can tell them apart is by saying what bond angle it is. And it also kind of helps us to remember what the geometry is. So this is our tetrahedral shape, and it has a bond angle of 109.5. So the next model that we're going to draw is simply 3 bonds and 1 lone pair. And we can take our current lone pairs are these electrons that look like this. I'll draw a set. So here's my example. It's when we say that there's 2, so that's a lone pair of electrons, meaning they're not involved in bonding.
So what's the triangle?
What do you mean triangle? Well, I'm trying to draw this in 2 dimensions, and that's my best bet at it. I got to be honest, when I draw Lewis structures, I draw it like it's in 2 dimensions, but what you have to do is trick your brain in saying, no, it's not 2 dimensions. That bond angle is really not 90 degrees, which is what it kind of looks like. Instead, it's really that 109.7, and it really has this weird tetrahedral shape. So if I rip off 1 atom and leave that bond sticking in there, that kind of represents those lone pair of electrons, okay? And we're going to call this molecule trigonal because it's kind of like got a little triangle. And then it looks like a pyramid, so trigonal pyramidal. And of course, the bond angle is still the same, meaning anything that has 4 bonds is going to be separated by 109.5 degrees and have that sort of tetrahedral as its base shape. Because the furthest apart you can put 4 objects in 3-dimensional space is 109.5 degrees. That's the idealized shape for that. That's what valence shell electron pair repulsion theory is simply saying. Put them as far apart as possible. Okay, what do you think we can do next? Just rip 1 more off. Go. So now what I'm looking at, and I'll continue that chart, so number of bonds, number of lone pairs. So I've got 2 bonds now and 2 lone pairs. And so if I kind of draw a picture of that, our classic example of that is simply the water molecule. So it's got 2 lone pairs on the oxygen. So one of the reasons, for instance, a lot of people, when I first start doing Lewis structures, if I draw water, they're like, why don't you draw it like this? What's wrong with the second picture? Yeah, this looks like it makes this 180 degrees. Yeah, like it's flat or linear, but this really is still 109.5 degrees. And so, no, the Lewis, you can draw it on paper like that, it's not wrong, but what you do have to realize is that really the reason I always draw it bent like this is because that's how it is, it's bent like that. And that changes some of the aspects of the molecule. For instance, when we start talking about polar and nonpolar molecules, Whether something's linear, kind of like this, or something's bent like this, they're both 3 atoms, right? Makes a difference. This is nonpolar. We'll find out that this is polar. So when we get there, we'll talk about that in a little bit more detail. And so we're going to call this molecule bent 109.5 because that's the bond angle, and it literally is bent.
Sounds like a radio station.
Yeah, let's get bent on the 109.5. Playing classic rock, brought to you by Dr. DJ McLaughlin or something. Dr. McLaughlin. Jam Master. I like that. Jam Master J, bringing you the tunes from Rangeley, Colorado. Okay, if I take one more atom off, realize that if I only have 2 atoms, do I really have a shape? There's no angle, right? To have an angle, you have to have 3 atoms at least. So things like oxygen, nitrogen, things that are only 2 atoms that are diatomic like that, don't have a shape. You have to have at least 3 atoms to have a shape. Okay, the next family, so this is kind of separate, meaning notice for the first 3, what did it all add up to? 4, right? We also have a set of things that add up to simply 3. So if I have 3 bonds, or I'm bonded to 3 atoms and no lone pairs, then I can have something like that. Now, unfortunately, the classic example of this, well, there's this example that is kind of normal. This obeys our octet rule. Notice that it involves a double bond. So here's where people sometimes get confused. That's not 4, well, that is 4 bonds, right? But remember, I said this is the number of bonds, and I really should write it, I guess, 2 atoms, right? Number of bonds, 2 atoms. There. And so notice that I have 4 bonds, but how many atoms am I really bonded to? Just 3 atoms, right? So that gives me this shape. Now, a lot of people will say that that shape and this previous shape look a lot alike. And they're not exactly wrong. They do kind of look alike, right? They look like little triangles, right? But there's differences. The first difference is that this bond angle here, since this is all in one plane, is 120 degrees. And so we call this trigonal planar. So realize there's trigonal pyramidal that actually literally looks like a pyramid, and there's trigonal planar where all the atoms are in the same plane, whereas the pyramid ones, some of them are below the plane of that carbon atom, right? So go ahead and if you want, build both models and sit and compare them. Because this is what you get on the test, right? You don't get your notes, you don't get anything else. Well, you get your cheat sheets and all that normal stuff, but this is what you get. And so this is how visually you're gonna have to be able to either tell apart these molecules, or when you draw them on paper, you're gonna have to say, well, the difference is this is 3 atoms and this is 3 atoms, but what else does this have? A lone pair, right? So too far away maybe. This? Which one am I showing? This? We haven't talked. Oh, red is oxygen for the models. Whites are the hydrogens. Green is usually like a halogen. Blues are supposed to be nitrogen. Yellow, I don't know what color yellow is. Sulfur, I think. Yeah, not everyone gets yellow. Mostly it's red, black, and white and green. Looks like it's trigonal planar to me. Now, the other way to draw that type of molecule is occasionally you'll have something like this, but what's wrong with this example? What's wrong with that example? It is trigonal planar, it really is. Yeah, it violates the octet. So occasionally if you're looking in books, they'll use that as the example for this. And it's a good example. I mean, this molecule really exists, BH3 exists, and if you try to draw the Lewis structure, what you realize is that there simply is only 6 valence electrons. And so the reason it violates the octet rule is there just plain old isn't 8 electrons around it. But we said we're going to try to avoid violating the octet rule. So I'm going to mention it, but our classic example is going to be just the carbon double bonded to an oxygen with 2 hydrogens as our trigonal planar.
It's up to you if you want to or not. I don't think you'll encounter it, but you might want to put it as just, you know, as a side note or something, you know, word to the wise or a caution or something like that. So just like with those other atoms, we can do the exact same thing. What happens if I just pluck off either one from the one that has 3 bonds to it, or I can take this and I'll just pluck off a hydrogen. Yeah, now we have a lone pair. And so if we take a look at this and follow our pattern, number of bonds to atoms. You should also note that this table is in your lab handout too, right? Does anyone remember seeing that in there? So I realize I'm spreading out over several pages, so sometimes it's not as easy to see. But here's 2 and 1. So notice it still is 3. So it still means it belongs to that Trigonal Planar family. And so a good example of this would be SO2. So SO2, oxygen. Actually, this is a horrible example because it violates the octet rule. Where's my good example that doesn't violate the octet rule? Yes, we mentioned that the bond angle is 120 degrees now for these types of molecules. No, you're fine.
Wait, keep it on there. Is that planar? What's this for?
That is for.
That's technically to get them off if they're stuck on too hard. Really, I didn't put them in the model kits. There's these little ones that look like this. I don't even know if I have one in here that's built. But instead of using the sticks, we can use what are called space-filling ones, where instead of using big, long bonds, you use these little tiny white things like this. And honest to God, you cannot pry those off unless you have very strong fingernails. And so that little tool is supposed to pop those off nicely. But I took those parts out of the models one year when I had my work study go through and reorganize them all. So I'm trying to find my example that doesn't violate the octet rule for this, but unfortunately, I'm drawing a blank. Darn it. Jay, you need to be smarter than this. You get to play with these all day tomorrow, or all afternoon tomorrow. So yes, you do are allowed to play with these. Man, everything violates the octet rule. Here, we'll use this one. O3 is ozone. Well, we've been drawing it like this. So there is an ozone molecule. And so we're going to call this bent again. So notice there's 2 bent molecules, but this is bent with 120 degrees. So notice that if you compare the one that has two bonds to atoms and 1 lone pair, and that tetrahedral shape that has 2 atoms and 2 lone pairs, that they'll almost look identical, right? They almost both look like they're bent. But remember, one is bent with 2 lone pairs, that's 109.5. One is bent with only 1 lone pair, that's what we're going to call 120.
Oh, that's the name of it?
Right, so bent 109 and bent 120, because it's the only way to distinguish the 2 bent models apart. And then, of course, if I take this and drop off 1 more, do I have a shape anymore? No, because we have to have at least 2 bonds to atoms. So the last one we're going to talk about is if I have 2 bonds to atoms and no lone pairs. So this is kind of like a new family. The classic example of this is carbon dioxide. Oops, there's no lone pairs on carbon. Got to put lone pairs on oxygen. And I draw it linear because really it is linear, meaning that bond angle is 180 degrees and it's linear. And if you draw the CO2 molecule where you're using the flexi bonds to 2 atoms, you'll notice that that automatically gives it that linear shape. The other way we can get a linear model or a linear molecule part to it is if I draw something that has a triple bond. For instance, if I draw carbon, carbon, and then a hydrogen on either end, that also results in both of these atoms having a linear shape. And so, let's see, where did I do with that one?
No, we just normally say linear is linear simply because there's no other molecule that can really be mistaken for that. Here. So take a look at this, very linear, right? So realize that when you drew your Lewis structures yesterday in class, who knows if you got the geometry even close to right. You might have drawn, because like you could draw this molecule. There's nothing stopping you from drawing this like this. You know what I mean? But we have to realize that physically it looks like this, right? So one of the reasons I give you the models on the test, one of the reasons we build all these is so that you start getting that idea that what's written on paper and what's physical is not necessarily the same. And it's sooner or later you have to trick your brain on paper to be able to kind of think about things in 3 dimensions as opposed to just the 2 dimensions that we draw things on paper. So you'll get to build all the molecular models you want in class tomorrow during lab, and you will be able to get to see the shapes and see how your pictures are. And then it's up to you whether you want to redraw your pictures occasionally. Like, you know, if you really did draw it like that, you might want to say, okay, now that I realize it's linear, I'll redraw it like a linear molecule. This right here, CO2. Oh, I just drew it different. Notice it's the same model. What I'm saying is what we draw on paper and what reality is, meaning this, is different. And so realize that if you drew, it's kind of like our water example. If you draw water like this, technically that's the correct Lewis structure, right? It doesn't really show the geometry, and so a better way to draw water is to kind of draw it like that to at least show that it's that bent shape, that it really is not linear.
But we're going to make more complicated.
No. You can draw it, as long as the Lewis structure is correct when you draw it, that's great, but the second question for every test is simply draw the Lewis structure. What is the shape? What is the bond angle? So if you draw it linear and you write bent 109.5, you get full points for it. And then the last question is going to be polar or nonpolar, and we'll talk about that in a second.
So
Jeez, Aaron, just totally cut Haley off.
how do you tell if the bent is a 109 angle or a
That's, so let's take a look. There's my bent 109.5. Well, that's not a very good example. Well, okay, this is our example. It's not the best example either. This is our bent 120. So this has bonds to 2 atoms and 2 lone pairs. This goes to 2 atoms and 1 lone pair. And so you have to do a little bit of math and counting in order to probably differentiate them. The other way is, I mean, after you build enough of these models, when you start to look at them kind of like this, to me, it's pretty easy to see that they definitely should be different, right? And I just have to remember the one that has 2 lone pairs came from a tetrahedral shape. That means they're all 109.5s. And the one with 1 lone pair came from the trigonal planar shape. And so that's 120. Yeah. The other way to realize, well, here's 1 atom, here's another atom. So it's bonds to 2 atoms, right? There's a bond to an atom and a bond to an atom, because we're talking about the shape around the central atom, right? The other way to remember it is that basically if everything adds to 4, then that's always a 109.5. If everything adds to 3, meaning bonds plus lone pairs, that's 120. And if it adds to 2, that's a 180. I think that makes sense.
Hey, Jay.
Yeah.
Question for you, really
Mhm.
quick. Let's go off topic. With the O3, doesn't oxygen not bond to itself?
I said that that's kind of a bad example too. That's ozone.
Okay.
Meaning I can't remember where I wrote the right example that doesn't violate the octet rule. Oh, I know. I have to draw an ion like NO3 minus, I think. Or NO2 minus, I mean. Okay, so one,
Wait, so what adds to 4 and what adds to 3?
just the lone pairs and bonds. So notice that this adds to 4, this adds to 3.
Okay.
You have to memorize everything we talked about today.
Okay.
So basically memorize the table that's in the lab handout. There's also a table that goes through this in your book. And you either have to memorize it or, like I said, make up a story. For me, it's easy to go, you know, tetrahedral, trigonal pyramidal, bent 109.5. Meaning, to me, there's some logic behind it. You know, if I rip one off, this is what I get. If I rip two off, this is what I get. So you can kind of have a physical story to go along with just memorizing all the combinations. And there's only 6 of them, so I don't think that's too outrageous. So let's take a look at more complex molecules, meaning that they have lots of parts. And we'll just pick on the one that we had drawn earlier because it's a good example. So for instance, if you were given this as a Lewis structure on the test, what I could ask as a question is simply, what is the bond angle around all the atoms that have bonds, or what is the shape? Meaning that that carbon has a shape, this carbon has a shape, and that carbon has a shape and a bond angle. And the part that you have to realize is that if you look at the entire thing, or you build the entire molecule, there's a ton of atoms there, and it gets a little confusing. So cover up part of it. If I'm really asking just the shape of that carbon, what I'm saying is that carbon has 3 hydrogens, and then I don't care what's over there. So I'm just going to call it R for the rest of the molecule. Meaning, don't let the rest of the molecule confuse you as to what shape that is. If it's carbon with 4 things attached to it, what is it? Yeah, tetrahedral. And it's 120, or 109.5. Sorry, I was thinking of the next one, which is 120. Oops, 109.5. Same thing for this little carbon atom here that's in the middle, and I'll draw this up to make it thing. If it's too confusing to have all that extra stuff, draw it like this. It's got a bond to oxygen, and then it's got 2 R's, meaning the rest of the molecule. And what shape is that? Trigonal planar, and we know the bond angle there is 120. So if having too many atoms or too much stuff on the paper confuses you, abstract it. Say it doesn't matter what all is attached to the next carbon atom, that there's 3 hydrogens attached to it or 10 million other things. The only thing we care about is what's exactly right there.
Unless there's 2 lone pairs in oxygen.
Right. There.
So that's 3 and 2, or
That's what?
3 atoms and 2.
Well, we're talking about the shape around the carbon, meaning it's bonded to one atom, oxygen, another set of atoms that we're representing as an R, and another set of atoms that are representing an R. There's no shape around the oxygen because there's no shape between 2 things. It's just, I mean, you could argue that it's linear, but that's not technically true. And in order to have a shape, you have to have 3 atoms. And so just because it has 2 bonds, or it has a bond to 1 atom and 2 lone pairs, we don't have that on our list because that does not have a shape.
But trigonal planar has to have 0 lone pairs.
Right, carbon has no lone pairs on it. The oxygen has lone pairs on it. And if that oxygen confuses you, just replace oxygen with R2. And then you see that there really is only 3 atoms attached to it. Don't let all the extra lone pairs, all the extra stuff attached to it confuse you. Focus on just that core atom. Same thing when you're building a model. If you've got a big complicated model like this, and you're asked, you know, what the shape is on something, realize that, yeah, this is second semester technically. Realize that I can figure out the shape around, say, this atom right here by saying, okay, pluck off all the extra crap on it, you know, and break it apart. I don't want to break it apart because then I'll have to rebuild it. Cody?
So like on the test, you'll just point to a certain part of it.
Or I'll tell you every atom, or I'll be more generic and simply say, if an atom has a shape, tell me what it is.
This is correct.
Yeah, that's the correct model for that Lewis structure.
Beautiful.
Job, Aaron.
Yeah. And see, notice how I draw it as linear, but really I should probably draw it kind of like a zigzag like that, because it really does zig and zag, right?
We'll talk about that second semester more. And of course, this one is also the same as the other side, so I'll just do that. So one last topic, and then we'll call it quits. Polar bonds versus either polar molecules, or sometimes we call them dipolar molecules. So a polar bond is an asymmetric distribution of charge between two atoms. Asymmetric distribution of charge between two atoms. Oh, dipolar molecule. So we talk about polar molecules. Some people will talk about whether something's dipolar. Some people will say, you know, and then of course the other alternative is nonpolar.
This is distribution.
Right, asymmetric distribution of charge between two atoms. And polar molecules are an asymmetric distribution of charge, so notice the same, but this is across an entire molecule. So one is between two atoms, the other one is across the entire molecule. And so the idea is that a polar molecule has to have polar bonds. But just because something has polar bonds doesn't make it a polar molecule. It's kind of one of those little logic puzzles, right? Just because it's A implies that it's B, but if something's B does not imply that it's A. I feel like we should go talk about Joe and his logic class.
The what?
Joe and his logic class. An example would be, for instance, if I just take a look at a carbon-hydrogen bond, this has a slight positive charge, well, actually, let's pick something better. How about, yeah, we'll go like this. So this has a slight negative charge. Wait, no, carbon has a higher electronegativity than hydrogen, doesn't it? So this is a polar bond, right? So that, remember, is the symbol delta. Means a small either excess. And so what we're saying is there's a small charge of a negative charge on the carbon and a small positive charge on the hydrogen, not like a full plus and a minus charge in an ionic molecule. So it's a weak example of that. So that's an example of a polar bond. But if I draw it as a molecule, meaning I have 4 bonds like this is a nonpolar molecule. Because if I draw the charges like this, it's not asymmetric. It's very symmetrical. There's a negative in the middle, and all the positives are on the outside. The other way to recognize or think about polar molecules is they have to behave like magnets. And so they have to have one end that's clearly positive and one end that's clearly negative. If they have 2 ends that are positive and 2 ends that are negative, that's not a magnet. Magnets have one positive end or one positive side of a molecule and one negative side of a molecule.
So that has polar bonds. But
Right. So this has polar bonds, but is a nonpolar molecule because of the geometry. So this is why we have to talk about molecular geometry a little bit. And of course, the reason we care about whether something's got polar or nonpolar bonds is that helps us determine what the intermolecular forces are between those atoms.
you said it's non-polar bond because of the what?
No, it's a polar bond
I know, but
and a nonpolar molecule because of the geometry, meaning that there's no clearly end that's positive and there's no end that's clearly negative. It's really a negative charge surrounded by a bunch of positives.
This is not a polar bond.
Right.
Where is the polar?
Okay, let's draw a polar one then, because that makes sense, right? So here's a polar molecule. For instance, if I replace one of those hydrogens with a chlorine, and I try to draw it kind of like it's the 3-dimensional shape. So, and here's again, determining polar and nonpolar molecules, building the models, honestly, to me, helps. And so if you take a look at the electronegativities, the hydrogens are slightly positive, and then the chlorine is definitely slightly negative because it wants those electrons in the shared bond more.
So how do you know if it's slightly positive or slightly negative?
So remember, this is the lowest
Oh, so it's
electronegativity. This is the element with the highest electronegativity. So the one with the highest electronegativity is going to have the partial negative charge. The one with the lowest electronegativity is going to have the partial positive charge. And so if I draw that kind of like a magnet, then this end is negative, and this end has 3 positive charges. But that really is a magnet, right? One end is positive, one end is negative. It just says that the 3 positive ones are tiny compared to the 1 negative one. Or build a 3-dimensional structure, and then if I orient it this way, this end is positive, right? Because that's the hydrogens. And this end is negative because that is the chlorine end. The other way to think about this, so one way is to think and draw magnets. The other way that some people like is to pretend it's like a game of push and pull. So the protons are pushing electrons, right? And the negative part is pulling electrons. So does that molecule move? If this part is pulling this way, right, and this part is pushing this way, then there's a net push on that molecule, right? Whereas if I go like this, and if the hydrogens are all pushing, well, does that molecule move if I push equally on all 4? No. So another way to think about polarity, or whether something's dipolar or nonpolar, is simply whether there's a net force on it or not, if I'm pushing and pulling. So another example of like a polar molecule would be if instead of 1 chlorine, I put, say, 2 chlorines on it. And this one's a little harder to picture. This is where I think building the molecules helps. So if I rip one off and I put a green one, and I go down here and I find me another green atom. This one's a little harder to see. This is why I like building the models. But if I kind of build my magnet and kind of orient it this way, then I've got a negative and a negative and a positive and a positive. And one end is clearly positive and one end is clearly negative. But again, I think to see the picture, you almost have to build the model. And it also works with the push and pull. If the hydrogens are pushing and the green ones are pulling, what does that do? Moves, right? I sometimes like the movement one the best. Some people like the magnets the best. You can think about it either way. They're equivalent.
So would you go on if it's polar?
Yep. Whether there's an asymmetric distribution of charge or whether there's a net force acting on it, meaning it would move.
so polar is it stays,
Moves.
and then non-polar is it stays.
Correct. Nonpolar if you push down everything equally. Okay, so let's take a look at just a couple more examples. Realize that anything that looks like this, meaning anything that's trigonal pyramidal, has to be polar or has to have a dipole. Because if I just rip off one of these, even if I have 3 the same, well, fine. 3 hydrogens obviously are positive, right? And a lone pair of electrons is obviously negative, so notice that that's always going to be. There's no possible way to make this nonpolar because of that set of electrons. They're never balanced. Same thing with a bent molecule.
Thing doesn't move.
Yeah, it does, because the hydrogens are pushing, right? There's nothing, and the electrons are pulling. That would move. Same thing with a bent 109.5. This has to be polar. Because you're always going to have whatever is attached here, whether they're hydrogens or anything else, is always going to be positive compared to two lone pairs of electrons, right? So this end is always going to be positive no matter what. This is always going to be very negative. And so, again, for the bent 109.5, you're guaranteed that it has to be polar. So there are some trends you can figure out. So really, the one that's tricky is if it's tetrahedral or not. And then if you look at bent 109 or bent 120, that's this. Well, this is positive, that's partially negative. That certainly looks like that. And so in this case, it's polar. But if you look at something like, say, well, I know this one violates the octet rule. But if you look at something like that, we're all the same. That's sort of saying that it looks like a magnet like this, where I've got a plus, 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 and a minus. This is nonpolar. I mean, if you don't believe me, go ahead and build them. But if I take a look at Trigonal Planar, and these are all pulling or pushing in the same direction, they again cancel out because of that 120-degree bond angle. But if I change one of them, if I make one of them an oxygen atom, well, now I've got two things pushing and the negative part pulls, and definitely the molecule moves. Or certainly you can see if this end of the molecule is positive and this end is considered negative, that that's polar.
Okay, so one more time, can you just say the difference between
Polar means that there's a separation of charge. It means that it looks like a magnet, meaning there's a positive side and a negative side, or there's a net push or pull on it. And sometimes we say that's a net force. A nonpolar can have separation of charge, or has no net separation of charge, has no net separation of charge. It does not look like a magnet. And the push and the pull parts cancel. So there's no net force. Well, this is what I mean by separation of charge. One part is positive, one part is negative. There's clearly one end of the molecule that is different than the other. Whereas here, and it's a little hard to see this, but I mean in 3 dimensions, if you actually look at the trigonal pyramidal, if all the positive is on the outside and the negative is on the inside, there's no magnet that looks like that. You can't make a bar magnet that has 3 negative all around the outside and a positive in the middle. It's just impossible. So you'll get practice with this again on the lab on Thursday. And what I'm going to suggest is that this lab will be due Friday. You guys will have plenty of time to finish it on Thursday. And so we'll make the lab due Friday. That way we can get it graded over the weekend. You can get some feedback on Monday. And I know we said the test is on Tuesday. I don't know, maybe it'll be Wednesday. It'll be one of those days next week before Thanksgiving. I just don't want to cover too much new material because we're technically done with Chapter 11 and we'll start in on some of Chapter 12 or 13 because we're skipping Chapter 12. Yes? Yeah, it cancels.
Oh, yeah.
What did you think it did? You guys should know that there are no camels in chemistry that I know of.
Jay, explain to me. I understand this one's a push. How come this one's a pull?
Well, I mean, that part is somewhat arbitrary. What we're really saying is that the hydrogens are pushing the electrons towards the carbon, right? Because carbon's more electronegative than hydrogen, right? The chlorines are pulling the electrons away from carbon, or you can think about it as carbon is pushing the electrons towards chlorine because it's higher on electronegativity. And so what you really have is a net flow of electrons from this side of the molecule to this side, a little bit, you know. Remember, these are little partials. It's a partial negative, a partial positive. It's not like this loses an electron and that gains an electron because that's ionic, but it's a little bit extra here and there. And I'll draw one last example for completeness sake. For instance, if I have a linear molecule like this is nonpolar. Because that's partial negative, that's partial negative, that's partial positive, but you can't have a magnet that has 2 negatives on an end, on the ends, and a positive in the middle. You just physically can't build a magnet like that. You show me a magnet that has 2 negative ends or 2 north poles, if you're thinking about magnets, and I'll steal it from you, bury you in the desert, and claim to have invented it myself, and become famous. And then, now if you have two different atoms, for instance, if we throw an oxygen on one side, and I don't know if this molecule really exists, I'm just kind of making something up, where, you know, this is going to be a partial negative. Well, is that a good example of a linear one? If it's not symmetrical, then linear ones can be, well, here would be a good example. This one we've actually looked at. So if I have something like this, where this is partial negative, that's partial positive, you know, in this case, because one end is clearly positive and one end is clearly negative, this would be considered dipolar or polar, we've been saying.
So what's the difference between dipole and polar?
Same word, different, no, same meaning, different words. So they're used somewhat interchangeably, depending upon the book you read and the book you teach out of. One of those annoying little things in chemistry, it's kind of like my one book calls double displacement reactions double displacement, the other book calls them double replacement. So I just say it doesn't matter what book we're in, we'll use double displacement. Same thing with those rules on electronegativities and determining whether something's ionic, polar, covalent, or covalent. Those numbers change depending upon what book you read and what website you're on. And so, you know what? I just made one set of rules to use in both classes and said, screw it. That's as good as any other set of rules that I can tell. Okay, that's it for today. So tomorrow you'll get lots of hands-on experience and you get to play with the model kits some more. If you guys could take those back to the other classroom for me, that would be wonderful.